And now moving on to our next session by Sudhir Reddy, who has been designing and developing highly available, scalable distributed systems for close to 2 decades at Flipkart and Yahoo. Joining Sudhir today is Jain Johnny, who is a part of the Flipkart cloud platform team and has been a part of 3 large data center deployments and contributed to the evolution of hardware and software stacks in FCP, that's Flipkart Cloud Platform. Today, they both will be talking to us about building a cost effective cloud infrastructure that can be applied to other systems to help reduce the overall data footprint. Let's hear what their insights about Flipkart's infrastructure journey, components design, and learnings in designing a cost optimal, highly reliable private cloud infrastructure. Over to you, Sudhir and Jain.
Hello, everyone. We are here to give you a sneak peek into Flipkart data centers. We'll most specifically talking about how we are making it, running it highly reliable, and also making it a cost effective. We will give you a brief overview of the Flipkart business and how that translates to infrastructure needs. We will talk about how we go about designing the data center and how we go about selecting some of the components of the data center and some of the choices that we make in ensuring that we get the cost advantage and maximum efficiency out of the infrastructure. Flipkart Big Billion Days has changed the way India shops online. In the last few years, we have seen significant growth in the user traffic. During these few days of the sale, we get maximum number of users from tier 2 and 3 cities, and we get a lot of new customer acquisitions during this window, and it just keeps getting bigger and bigger. Flipkart regularly runs a lot of flash sales, and during this short duration, there is a huge spike in traffic which comes to us, and a lot of users place orders in that short duration. And over time, Flipkart has been launching very innovative features like voice assistant, engagement things like videos, games, and also new domains like Flipkart Quick. Right? All of these leads to significant growth in the market. So as of now, the Flipkart business scales around 400 million users, 15 million products, and we handle daily millions of shipments. How does this translate to the infrastructure requirements? We need to be very flexible in infrastructure capacity provisioning for handling this kind of dynamic BAU growth. Our peak compute variation is anywhere between 2x to 10x. And today, our external core systems handle million requests per second. At the same time, we have to be highly reliable and available. And we should be able to sustain any kind of user, systemic, or naturally triggered catastrophic events. All of this, and most importantly, we have to run everything at a very cost effective, giving us the maximum return of investment on infrastructure. As of now, to handle the Flipkart business scales, we provision millions of cores, hundreds of GPUs, and handle exabytes of data. And our internet connectivity to the public world internet is hundreds of Gbps. Let me give you an evolution of the data center story in Flipkart. 2014 was a very historic, big landmark in Flipkart history. This was the first time we ever went with the Big Billion Day sale. At that time, we were evaluating public cloud vendors who were available in India to see if they can satisfy our requirements for the scale growth. And what we found out is both in terms of cost as well as scale, they were not up to the mark for us to operate in the public cloud. So in 2015, we built our own private data center in Chennai. We had a large capacity expansion. We built our own in-house infrastructure as a service, platform services. Some of them were built during that time, and over years we have developed them. In 2018, we built our second data center in Hyderabad for business continuity reasons. And we built it with much lower capex, which is capital expenses, and lower opex, which is operating expenses. And that was primarily because we had exclusive partnership with some of the manufacturers directly and were able to procure cheaper, greener energy. And now in 22, we are building our new data center in Chennai and replacing the existing Chennai data center. We have worked with the DC facility provider closely. We have worked with them in design collaboration and also in optimizing the power usage efficiency. When someone says data center, what is the first thing that comes to our mind? Servers, lots of servers stacked up in rows of racks, right? And all of them connected together with network cables. But there's a lot more to data centers than just these things. There are a lot of mechanical, electrical, and plumbing devices which help in running this data center effectively. Things like chillers, cooling towers, precision air handling units, fire storage tanks, transformers, generators, UPS, power distribution units. All of them have to work correctly, efficiently to ensure the servers are running properly as in the right set of cooling environment. So monitoring these systems is absolutely important for us, right? From the temperature to the flow to the pressure to the voltage. All of these components are real-time monitored in our building management system. And not just these, even the physical security of the data center is of very important to us. And these are closely monitored in a real-time dashboard for us. Data centers are classified into multiple tiers based on their availability and fault tolerance, with tier 1 being the worst and tier 4 being the best. Tier 3 data center is one of our Chennai data center, which we have today, is a tier 3 data center, and it has a 99.982% uptime, which means it annually can go down approximately 1.6 hours. Whereas the new Chennai data center and the Hyderabad data center we have is a tier 4 data center, which is expected to go down approximately 24 minutes in a year. And tier 4 basically achieves this by having 2n system component redundancy, which means if n is required to handle the required functionality, we have twice the system components required there, are enabled there, and all of them run in active mode. So fault tolerance is an absolutely important key thing which goes into our data center design. So let's see how we enable this in our tier 4 data centers in some of the components. This is an electrical system. So if you see the top, we have the source grid from where the current power supply comes to our SD source in the data center. From there, it goes to the transformer. From there, it goes to the main LT panel. From there, it goes to the distribution panel. And then we have a UPS system and then the power distribution unit, which enables the power supply to the servers to handle the required capacity. So only one set of these components are sufficient to run the entire server load capacity. But to enable fault tolerance, we have 2n redundancy, which means each of these components are redundant. We have 2 of them in the data center, and a failure in any one of them can still work functionally for us and will not impact our data center in any way. For example, the source power which comes into the data center, we have 2 different geographically distant grids which supply the power. So even if one of that goes down, the other grid supplies the power to the other HD source transformers. If the transformer A goes down, the transformer B within few seconds automatically kicks in and feeds to the other LT panel, and the load gets distributed. Similarly, if both the transformers goes down, right, at the same time, we have the DG systems which kick in and automatically start supplying power to the data center. Now, if one of the DG system goes down, the other DG system is still capable enough to handle the required capacity for us. And if both of them go down at the same time, we have UPS systems running there for a certain time, which can help us continue the load at the same time. So if you look at this, in every component, there is a redundancy built in to handle the fault. Right? Going to the mechanical system, this is a heating, ventilation, and air conditioning system. Right? It consists of a cooling tower, a chiller, and a thermal storage tank, and pipes which connect to the precision air handling units which are residing in the server room. So if each of these components is again redundant, we have 2n or 2 times the components that are required to run the to cool down the server rooms. And if cooling tower 1 goes down, the cooling tower 2 kicks in automatically and works seamlessly for us. If chiller 1 goes down, the chiller 2 is there to handle the required capacity to cool down the water flowing into these pipes. And if both of these chillers go down due to power failure or temporary failure maintenance, the thermal storage tanks are having enough storage capacity for cooled water to be circulated into these air handling units for a limited duration and still be able to handle it. Similarly, the pipes which are connecting these are also redundant. So if you look at these, maintaining any of these components, it makes it very easier for us to take it down and still continue running the data center without having any failures. Now coming to the main server rooms, right? So we today have physically into 2 different hall rooms. So these are isolated from fire safety reasons. So fire in one cannot spread easily to the fire in the other hall room, right? And the right from the power supply to the heating and ventilation systems, all of these are totally isolated in these. So these are geographically co-located, but you can treat them as independently different data centers. Right? So we call them as zone 1 and zone 2. Now, within the zone, what we have is servers. We design the servers in such a way, in the rack space in such a way that we have cold aisles and hot aisles, and the cold aisle is circulated between the servers, and the hot aisle is taken out from there and recirculated back via chillers and cooling tower to the hall room. And this helps us in cooling the system very effectively, and it helps us in reducing the overall cost of operating the data center. Right now, coming to the networking thing, right? So when a user connects from his device, he connects via internet to us. So we have multiple ISPs. We are partnered with them, and each of them have multiple paths, which are geographically distant paths, which connect to a data center. So failure in any one of those pipes, network pipes, still doesn't impact us. Similarly, between our data centers in Hyderabad and Chennai, we have the same thing where we have multiple paths, physically, geographically distant paths to reach to the data center coming from multiple ISPs. So this helps us in having a fault-tolerant, redundant networks, and we over provision the required capacity that is needed to handle this, so that we can handle any kind of failure in these paths. Not just external to the data center, even within the data center, we have redundancy built in at multiple layers. So our internal network is a class 3 tier network with super spines. What it means is on the racks, there is a leaf node, and the leaf node is connected to multiple spines, to all the spines within a pod. A pod is a group of spines and leaf nodes and racks. So for us, we can scale the data center by adding more pods. And to, to ensure connectivity between these pods, we have super spines which connect these spines. So failure in any of these spines still allows us to connect to the other spines in the data center. And then failure in any of the super spines, because each of the spine is connected to every other super spine. So redundancy is built into this layer also. Failure in any of these components doesn't impact us. The only failure which is not handled is the leaf node, where in the leaf node goes down, probably tens of servers would be will not be connected to the network. And there also the fault is limited to those servers, and we should be able to still survive those failures. So if I were to summarize it, we have thought through fault tolerance at multiple of these system levels, right? And that's how we are able to reliably run the data center. Now, Jain will talk about how do we go about selecting some of the hardware components.
Thank you, Sudhir. Before getting into the selection of components, let's analyze the cost of running a DC and what contributes most to it. The two major contributors are the floor space and the power. Each of them is roughly 45% of the total DC cost. The cost of DC space is decided at the time of the build out and is kind of fixed. We try to maximize the number of racks in the available space, but also leave some free space in each rack for future expansion. For smaller capacity expansions later, it will be much cheaper to use the reserved space in each rack than building a new floor or a new DC. Next, if we drill down to the power cost, we can see that more than 70% of it is by IT equipments, which includes the servers, storage, and networking gear. Among those three, compute servers are the majority in numbers and contributing the most to the power usage. So takeaway is if we have to optimize the DC power cost, we have to optimize the compute servers. Now let's drill down into a compute server and see the component level power usage. The main contributor, of course, is the CPU, and after that is the overheads due to cooling devices like fans and losses in the power supply units. So it is important to choose efficient CPUs, power supplies, and fans. In the right side graph, you will see the power consumption in one of our servers, how it varied across different loads. When we increased the load from 20% to 80%, which gave four times the more throughput, the system used only about 25% more power. Keeping the server load high also ensures that the power supply and the cooling efficiency is also improved. So just choosing efficient components is not enough. It is equally important to run them efficiently. So here are the major considerations while choosing a compute platform. One is the core density. More number of cores per server will reduce the bin packing wastage and also reduces the DC space requirement. So we can either build a smaller DC space or leave more free space in the racks for future expansion. Next, we have to reduce the capex. CPU performance per dollar is the main metric here. And also, we don't prefer to use very high TDP CPUs as they will require larger power supply and larger heat sinks and high RPM fans to cool them, all of which will in turn increase the cost of the server. We also need the system to be power efficient. So we have to consider the CPU performance per watt and also choose efficient power supply units. The right side graph shows an example comparison between two Intel Ice Lake Platinum CPUs. The list price of the red CPU is about 60% more than the blue one and takes 30% more power, but it provides only 20% more core density and performance. Also, the red one needs bigger power supplies because of the high TDP and needs better cooling. Out of these two, our pick will be the blue one for better capex and efficiency than the increased core density or throughput. When we select a CPU for our DC, we need to understand the architecture and features of it. Also, we need to see how it impacts various workloads. This will help us decide if we can go with a more homogeneous deployment or if you need to deploy different CPUs for different use cases. Now let's look at the main factors that can impact the workloads. First is the CPU design itself. For example, the monolith design in Intel scalable processors versus the multi-chip module or MCM design in the AMD EPYC, which can decide how we need to schedule VMs and also the bin packing. Next, the size and design of the CPU caches. For example, the large unified L3 cache in Intel versus the much larger but segregated L3 caches in AMD, which can impact database performance. Then the count and speed of the memory channels in the platform, which decides the possible core to memory ratios. The PCA slot, the number of PCA slots in the platform, which decides how many peripherals we can connect to the system. In future as well for expansion. Next is the core-to-core latencies, which vary significantly in AMD multi-chip design. And if the workload is not pinned to the right set of cores, might impact the application performance. The core-to-memory latencies, which help us decide how many NUMA nodes we need to configure per socket, and that can also impact bin packing. And finally, the need for certain special features like the AVX 512 in Intel for faster compression, encryption, etc., and the secure encrypted virtualization in AMD for improving the application security. Now let's see what we do to compare different CPUs in terms of performance. We measure the single thread performance and overall system throughput. We use the spec CPU benchmark suite and determine how it will work for both single and multi-threaded applications. We measure the throughput versus latency curve, like the spec JBB result we have shown here. We also measure the total power versus load curve, like we have shown in a previous slide. We also use stream benchmark to see how memory bandwidth scales with the number of cores. So in summary, this is what we do in selecting a compute platform. We consider the CPU and platform design, the cost, power efficiency, and performance. Now we move on to the storage selection, because more on the performance, reliability, and availability. We have to cater to different use cases, and hence we have different storage deployment topologies. About 90% of our storage is used by large databases and big data systems. These systems need larger disks and also need better availability during any planned infra maintenance. We use dual path JBoards or JBoFs for this use case. And this diagram is a logical representation of this topology. We have a JBoard with dual controllers, and multiple servers are connected to each of these controllers. These servers are also equally divided across racks. The advantage of this kind of deployment is that we can migrate the workload from one server to another in case of any path failure, be it JBoard controller, cable, server, or the top of the rack switch. This way, we provide high availability for storage infra during both planned and unplanned maintenance, and avoids large-scale data copy or rebuilds in the application layer during the maintenance. The second use case is the low latency database for caches where performance is more important. We use locally attached NVMe SSDs, and it is only about 1% of the total storage. So application level rebuilds or copies can be tolerated during a maintenance. Last is the boot disk and temporary scratch space. Basically, any type of storage will work for this, but we use locally attached SATA SSDs or hard disks to keep the deployment simple and cost down. Now, here are the major considerations while choosing a storage media. First is the performance to cost comparison, where we calculate the IOPS per GB and the latency versus IOPS curve, like the graph shown here, to compare different models. Next, to determine the disk size, we compare the cost per GB of various models and also choose the endurance we need based on the workload requirements. For example, earlier we used to purchase high endurance 3.2 TB SSDs, and when we analyze the usage pattern over many years, we realize that 99% of our SSD use cases do not need that level of endurance. Then we moved to lower endurance 3.8 TB SSDs, and we got about 20% more space for the same cost. Next, for the high availability in the JBoard or a JBoF kind of deployment, we need dual ported disk, and for the locally attached case, we use single ported disk. And that's it in the storage selection, where the focus is more on the availability and performance while keeping a check on the cost. At last, I would like to discuss some of the constructs we have, which improves the availability of both compute and storage services in our DC, especially during a planned maintenance. When we have to do a large-scale maintenance in the DC, we divide the DC into smaller maintenance units. For storage nodes, it is done mostly statically based on the physical location of the node. And for compute nodes, this is mostly done dynamically by looking at how different services in Flipkart are spread across the servers in the DC. Then we schedule each maintenance unit, send automated notifications, and execute the maintenance. To ensure availability for a given service, each maintenance unit will contain only about 5% of the nodes running that service. For stateless applications, this is taken into account when we dynamically define the maintenance units. And for stateful services, each static maintenance unit is about 5% of the entire DC. We also do VM migrations for stateful workloads, which are actually running on the JBoard storage, like I have mentioned in the previous slide. So that even the 5% capacity that is going down for maintenance will not see a significant downtime during the maintenance. Then we have a concept of instance groups to deploy services into a set of nodes as a single unit, so that when individual nodes go down, individual nodes in the group go down for maintenance, instance group can be resized to get back to the original capacity. The same logic applies to Kubernetes containers using the stateful set and daemon set constructs. We are aggressively moving our service into Kubernetes to take advantage of these constructs and using operators to handle maintenance events automatically. Recently, we have started to evaluate durable block storage or software-defined storage to protect applications from media failures as well. They also provide better workload migratability during compute node maintenance, as the storage volume can be accessed anywhere from the DC. Unlike the current JBoard deployment, where storage volume is accessible only within a limited set of servers. With this, back to Sudhir to discuss some of the measures we take to maximize the cost efficiency in our data center. Thank you.
So new hardware doesn't mean it is better for us, right? So we have to do a right trade-off between performance and cost. Like Jane mentioned that we do some deep evaluations to figure out at what performance are these comparable and what is the cost, what is the power consumption for these system components, right? So based on that, we do pick between the chips that is available across vendors as well as within the same vendor, different families of these chips, right? What we try to do is we try to pack more cores into the same servers so that we get higher core density. And similarly, we try to pack more servers within the same rack so that we could have more compute density within the same data center. This helps us in improving our overall allocation of resources. We are also looking at composable infrastructure where the components are available in the data center and we could dynamically compose them and meet the requirements of the application, right? So some of the things that we have done right now is attach the storage on the network and see how we can improve the utilization of this and reduce the overall cost of the storage itself, right? So we have right now done very limited work on this one, and we're looking forward to do some more experiment with some more things in this space. So coming to the capex cost, right? It is a significant cost for our data center. Capex is the capital expenses that we do. So we have partnered with some of the manufacturers directly and have sourced the components from them. And then we have custom designed our infrastructure. We get it assembled from some of the manufacturers and we bring it to a data center, right? And these are very specialized custom solutions for us, which helps us in reducing our overall costs and running these in a more efficient manner, right? And one of the significant component for us is the operating expense cost of the data center. And power consumption is a very, very big factor in that, right? Like Jain had mentioned sometime in one of the slides. So improving this energy in the data center, energy consumption in the data center is very important. So power usage efficiency is how much amount of power is actually consumed by the IT infrastructure. And that is where we want most of our power to be going to, right? So every few years, like 5 years, we build a new data center and end of life of the existing data center. Like the Chennai data center we have today, we are replacing it with a newer data center, which is much more efficient in terms of energy consumption, or having the newer equipment to handle better resilience into font failures, and also give us more ROI to our investment. Coming to infrastructure as a service layer, right? Today within Flipkart, we have provision to have any type of flexible instance sizes. We have close to 100 odd published instance sizes, which we give it to the end users. So these depend vary from the workload to workload to help us optimize on the right instance sizing. For example, someone can ask for a Redis server, a single core with a large memory, to someone who can come and say, I need Aerospike for Aerospike 16 cores with, let's say, 30 GB RAM. Or someone could come and ask different size of terabytes of disks that they want to attach. Or for big data workloads, they could be asking for a totally different type of instance size. So this helps us in providing the right instance size for the application developer to figure out what works for them and use that in a very easy manner for them, right? And it will, with having efficient bin packing algorithms, we try to minimize the infrastructure wastage that we go through and help in utilizing the hardware more efficiently. Also, we have started the journey to containerization. In the last BBD, some of our critical workloads were running on Kubernetes using Docker images. So we are heavily invested in moving to Kubernetes. Most of our stateless workloads are planned to be moving out to Kubernetes by the end of next month. And we are also looking at moving our stateful workloads to this. So by using the right constructs in the Kubernetes and autoscaling capabilities, we have experimented and seen 2x utilization of the CPU resources, which helps us to pack more in less space and use more resources efficiently. Right. So we're also looking at how do we reduce the virtualization overhead. So we look at some of the virtual I/O operations, which can help us in optimizing, directly leveraging the device functionalities and exposing it to the virtual machines, applications inside the virtual machines. Also, by moving to containerization, we're removing the overhead itself. And we're also looking at running Kubernetes itself on the bare metal, which will make it more efficient and optimized. And we will waste less resources and overall help in improving the cost of running the data center. Coming to the application layer, data tiering and retention is absolutely important. Today, a significant portion of our spend goes towards storage, and especially for the big data systems, right? So we do very aggressive tiering in the data center, at least for the data platform. So we move data from hot tier to warm tier and to cold tier very aggressively. While all the data is still accessible by the users, what helps us is in reducing the compute costs in having less data in the hot tiers, and additional latency from these cold and warm tiers is acceptable to the users, because these are batch jobs. Similarly, in the application DBs, people are working on making it in a multi-tier data storage systems where the hot data is in a system and the cold, after some time, the data is moved to a lower tier, right? So this overall helps in reducing the cost of the storage and compute footprint. Uh, we have heavily invested in managed services. We have today centrally managed object storage, centrally data platform is centrally managed. We have centrally managed queuing as a service. We have key value store, which we're working on. We have distributed SQL as a service. We have centrally managed MySQL services. So all of these services helps us in consolidating the hardware, which is spread across the teams and not used efficiently by over provisioning it and other things. They end up wasting these resources. So by consolidating it, we get the advantage of upgrading it to the latest performing versions. We get the best of the features, reduce the operational overhead across teams for maintenance, and we also are able to utilize this hardware much better and in a higher percentage utilization in terms of both compute and storage, and hence gives us better ROI. Um, Application developers in Flipkart continuously measure, monitor, analyze, and optimize their tech stacks. They end up rewriting using newer frameworks, newer technologies, or upgrading their DBs to a latest version, which will give them significant performance boost. Right, and every year before the big billion day sale, where there's a huge spike of resource requirements, which is going to hit us, uh, these application developers try to see how they can squeeze the maximum out of their application and reduce the overall infrastructure footprint growth rate itself. Right? And most importantly, I think billing and recommendations is an absolute important thing in a data center, where we surface out how teams are using the hardware footprint for their different services, not just in the VM world, but also in the managed services world. If we can provide them a view of how their trend has been over time, how their growth rates has been, how they're efficiently are they utilizing, and what are the optimizations they can do in reducing the overall footprint, it will significantly help us in controlling the costs of running the infrastructure. And all of this combined together is what is helping us and helping us reduce the operating costs and improve the efficiency of the infrastructure that we have invested in. With this, we'll be happy to take any questions. Okay. So I'm just going through the questions. Just give me a minute. One of the question is, how do we recycle hardware? Is there any automation around it, especially with newer architectures being available at rapid rate? So if you're talking about physical hardware today, so we have a lifespan of these hardware, and today our Chennai data center hardware is close to end of service contracts, warranties, and all that, right? So we are building a new data center, which is where we'll set up a newer hardware, and some of these old hardware, if they cannot be reused for us, we would dispose them off to vendors. And yeah, yes, and the new hardware, right? We try to see that we run it for the lifetime of the data center, right? And over time, if we procure hardware during that which can be reused, we ship it to the other data center with a minimal cost overhead. And Jain, do you want to take the other question? Like, what is the difference in Intel versus AMD?
We do see a lot of differences in terms of performance for different various workloads. But it will be I mean, in a blanket statement, it will not be safe to say one is better than the other, or AMD is better than Intel, or Intel is better than AMD. it will be very workload specific is what I will say. So each of it's like if you're running a database, you need to uh, benchmark it against Intel SKU, which is of interest for you, and the AMD SKU, and then compare the performance difference. There are certain areas the AMD is working better, and certain areas which Intel is working better.
The question is, how do we get hundreds of Gbps bandwidth from a data center? If you're talking about public internet bandwidth, we have multiple connections with ISPs, which run into not hundreds of gigs Gbps. It is 100 Gbps, close to 100 Gbps, I believe. We have inter-DC bandwidth itself, which goes upwards of 50 Gbps. This is the bandwidth between the Chennai and the Hyderabad data center, which is not the user traffic. Okay, the next question is, how do you guys decide to go ahead with own DC instead of public clouds? Well, public clouds, the cost factor is a significant factor. Like I mentioned in 2014-15, none of them in India were able to scale, and the cost of them was not viable to us. Today, also, we have a partnership with a public cloud vendor, and we do leverage some certain things on the public cloud. That said, we're also looking at hybrid cloud going forward, where we may have some of the significant portion of the infrastructure running on the public cloud. Right now, if you were to ask me, the key decision points for anyone to make this choice would be one is the cost factor, which is the total cost of operating it there. And second is the productivity ROI return that you would get by leveraging this infrastructure. Okay, I think that's it. Thank you all for giving us your time and attending the session.